I'm Alex Bradbury. I'm a co-founder of a lowRISC project, and seeing as there's a number of people who hadn't heard of it before, speaking to you yesterday, I'll just give a very brief summary of what we're aiming to do and what we're aiming to achieve. So fundamentally, we're a not-for-profit project which aims to become something like the Linux of the hardware world. We want to take existing open source IP, add and develop it, and produce a fully open source system on chip in volume, which is available for people to buy. This, of course, has advantages as a platform for other people to base derivative designs, and it actually kind of follows on from our experience with the Raspberry Pi project, which a number of us were involved in. I did a lot of engineering work on the software side. Rob Mullins, who's a fellow co-founder, was also a founder of Raspberry Pi. And with that project, which was obviously targeted at the educational market, we found that there was a massive community worldwide of hobbyists, of people who are interested in computer science and computing, who want to contribute to an open project, and that there seems to be this kind of untapped market for people who are interested in open source technology. Because, of course, with that project, you're stuck with a proprietary system on chip, and we felt there was an opportunity, particularly when we found RISC-V after we started the project and we evaluated the choices, to kind of try and do better than the status quo. So our ultimate goal is to produce what we call a kind of Raspberry Pi for grown-ups, so a low-cost development board available for people to purchase. Ultimately, we'd like to be in a situation where we're self-sustaining and we're able to maintain regular tape-outs. Ideally, we'd have a tape-out, say every 2 years, every 18 months, so that if you as an individual contributor or a research group who's working on a new feature that you want to get upstreamed, you know that if it's accepted and people agree that it's a worthwhile change, that in some reasonable time frame, you'll be able to actually get access to that technology in a real shipping CPU. And of course, this is a project which would be impossible just alone. We've already benefited massively from working with other groups, with the ETH team who are working on Pulp, with the Berkeley team and their rocket base design. And it's the only way that we're going to be able to reach our goals. In terms of licensing, we're sticking with simple permissive licensing for changes to the upstream Berkeley code. That's, again, using the BSD license. We're interested in looking at something which is Apache-derived in order to have some patent protection provisions, but we're sticking with simple licensing that makes it very clear that you can take the implementation, use it in your own projects, your own products, your own research, and there are no restrictions on what you can do. So before I look forward to what we'll be doing in the coming year, I thought I'd just have a very brief look back at some of the milestones from last year. As I mentioned previously, two of the technical focuses that we're particularly interested in are flexibility and security. So one of the ways that we're looking at implementing this was in support for tagged memory. Now I believe we'll have a talk from another group about some of their work on tagged memory or extra metadata. So the basic idea is just that every 64-bit word has extra metadata associated with it, say a few bits to offer fine-grained access permissions, and combine that with a software security policy. You can use that to implement more fine-grained control on access to memory, or potentially other uses, such as debug or performance monitoring, if you trigger certain events or when certain tagged values are accessed, because you effectively now have infinite hardware memory watch points. And so if you look at our website or look at our previous RISC-V workshop talks for a more in-depth discussion of what we've done, we have a very detailed discussion of what we're implementing, what we have implemented, and an FPGA-ready version for you to download and have a play with. And Wei is going to be talking about the most recent milestone, which is untethering the SoC today at 11:15, so I won't spoil his talk. You can hear more about that slightly later. The other thing that we had going on, I thought I'd highlight a few projects that perhaps you might not be aware of, because I think a number of people here might be quite interested in the outcomes. We were a mentoring organization in last year's Google Summer of Code, so we were able to support a number of projects and then found some funding for a few more as well. So to pick just a few of them, I think Arun mentioned yesterday that we have a SEL4 port to RISC-V, which is a formally verified microkernel, or at least the base unported design is formally verified. It hasn't yet been formally verified on RISC-V, but that may well be an interesting base for a number of you looking at various projects. There's also work done on porting a open-RISC JavaScript emulator written in JavaScript to RISC-V, which is one of the highest performance JavaScript simulators, and also some very cool work looking at what's called rump kernels, which is where you're able to take the NetBSD kernel and use elements of a NetBSD kernel as a library. So in this case, we were looking at reusing NetBSD's TCP IP stack, running that TCP IP stack on a separate RISC-V core. So say like we have these small minion cores, and just as a proof of concept, looking at using that to implement something like a old school TCP IP offload engine, but with the advantage that where you'd offload your TCP IP to a separate processor, but unlike many previous commercial offerings which have fallen out of favor, you don't have a unmodifiable proprietary software stack running on that you have no ability to patch. So I'll shortly tweet out links to previous presentations about those projects. So if you have a look at our Twitter feed in about 5-10 minutes, then you can find more about what we did or talk to me later. And so looking forward to what we hope to achieve in this coming year, the first thing will be continuing with the untethering work, which involves some kernel changes. One area where we'd welcome community involvement and advice is replacing FPGA vendor-provided IP with vendor-neutral open peripherals. So if you have particular experience, that would be very useful, particularly as it's useful for people who want to use it as a FPGA prototyping platform. It's not useful as part of our key goal of moving towards an ASIC tape-out. So we're very keen to have people who are more interested in the FPGA platform to help us out there. Something else I'll briefly mention, which again Arun touched on yesterday, is the next thing we want to add is an interrupt controller. So I had a mailing list post that seemed to get some good feedback a couple of months ago about potentially using the Berry programmable interrupt controller as a base for this. And I'll just simply restate the argument here, which is that I'd argue that there's absolutely no point in us spending lots of time on defining a standard programmable interrupt controller for an application core that doesn't take into account potential optimizations for virtualization. The virtualization specification for RISC-V doesn't currently exist, and it's not going to exist in the near future. Therefore, it would make sense to pick something as an intermediate standard or a de facto standard, something for those of us who are, want to reduce effort on porting of Linux FreeBSD, and where we can. And Berry has the Berry pick, which is another University of Cambridge project, has a nice property that it's been used extensively on a multi-core FreeBSD system. It's well documented, has everything you need for a multi-core FreeBSD system. So it seems like a sensible starting point. I'm not entirely sure how well it would scale down to a microcontroller class system, though Sam, who many of you will have spoken to yesterday with his Kestrel project, I know has had some ideas on scaling it down to smaller systems. Now, the big thing that we're going to be achieving by the end of this year is taping out our first test chip. And so the thing that we're hoping to prove with this is the integration of third-party IP, because of course we're deriving from the Rocket core for our application cores. We've added tagged memory and some other things. Hopefully we'll be deriving from the Pulp cores for our Minion cores, which for those of you who haven't encountered that before, what we call our Minion cores are just small microcontroller class cores which are used to implement low-level things such as soft peripherals for SPI, I2C, potentially other uses, because it's part of trying to provide a more flexible platform. So both Pulp and Rocket have been silicon proven multiple times, so the extra bits that we're adding is as well as these new features, is integration of third-party IP, so a memory controller and PHY, USB controller and PHY. So I sketched out some target specifications here. Now, of course, all of this is subject to change. It's not finalized, but I wanted to share what we're currently heading for feedback, thoughts, views. So we're looking at a 3x3 mil die on 28 nanometer. Packaging is IC packaging is an interesting issue. I'd love to talk to anybody who's got experience there. We're currently looking at using a wire bond BGA package, both for cost reasons and because we're currently just about to finish a tape out of a 40 nanometer test chip on a separate research project, a 128 core system, and there we're working with Michael Taylor at UCSD, who has a package he's designed as being reusable. And it doesn't explicitly support memory interface, but it may be able to do so with minor changes. So that's one potential base, but I'd love to talk to any more of you who've got experience there. And of course, in addition to the minion cores, I mentioned that you'd use those to implement potentially, as Ron said yesterday, you might use it for system management type features or for low-level I/O. We also talk about having what we call a shim, which would be a small piece of logic to offload the very kind of dumb bit-banging things that you don't want to do in software, such as shifting out a register. The other point that's definitely up for discussion is this aspect of interfacing to FPGA. Again, I'd welcome any feedback. And this describes gives a rough view of a potential implementation for a test chip. So for what I show up here for how the minion cores are connected to the main bus, there's obviously a massive design space for how you might communicate with the minion cores and between the application cores and minion cores. We've spec'd out something that looks like a sensible starting point, but as both an engineering task and potentially through our research work, we'll be looking at different options for providing that interface. Now, to say a little bit about third-party IP, as I said before, our ultimate goal is to produce an open source system on chip. And this would involve having all the digital logic being completely open source, but this isn't something we can do at day one. Much like the GNU project started out with the ultimate goal of having a fully open source Unix implementation, they work piece by piece, replacing different aspects with open source implementations as it made sense. And we're taking a similar approach, which is why we'll be using commercial USB and memory IP. We are interested as a general platform feature at providing what you might call hardware firewalls or wrappers, which would actually be useful for any IP, open source or not, in order to provide some simple ability to lock down access to the memory bus, such as limiting the ability of that piece of IP to deliver certain requests. Put this last point just in case I'd be interested if anybody has a alternative view, but as I said, our goal is all digital logic being completely open source. I don't think there are any analog engineers here, unless I'm mistaken. There's one, but there seems to be much less potential for having open source analog IP, both with issues of the economics of that, with it being process technology specific, plus, of course, the vendors being very, very protective of details of their process technology. So a quick rundown of the things that we'll be working on in this coming year. So we mentioned we had a tagged memory release with the untethering. Work on that kind of was done on a different branch, so we'll be reintegrating that and implementing the designs that we have for further optimizing the tag cache. We'll be integrating the pulp-based minion cores along the lines of the diagram I showed earlier. And we've got a contractor who's about to start work on this shim that I talked about, which I'll be able to present at the next RISC-V workshop, I should think. And then, of course, integration of third-party IP is one of the major goals. Another thing that might be interesting to chat about is benchmarking performance analysis. We've had I think it's come up a couple of times before. I personally believe strongly that a open source processors and an open source ISA deserves a fully open source benchmarking suite rather than relying on proprietary suites where you have limitations on the numbers you can share or you just have to pay to get access. So we've had some funding for a number of students working with us over the summer, but I'm happy to chat to people before that where we'll be putting some effort into both benchmarking and profiling particular use cases on a rocket-derived core, and depending on the interests of the students and their ability, looking at perhaps publishing some case studies on, given this application, given these initial performance results, how you might go about optimizing or customizing a RISC-V design by adding extra instructions, adding an extra accelerator, adding extra accelerators, or making compiler changes, and so on. Another call out I'd make is to Stefan Lentowitz's trace debug work. So unfortunately, he's not over here, but he's talked about it previously at ORConf in Europe. So he's done lots of work on trace debug on his research project, OptimSoc. And I believe he's spoken on the mailing list on the discussions about run control debug there. But I think an interesting base starting point for a standard RISC-V trace debug system. So he's got a website where he's got some initial details if you want to have a look. So in conclusion, I'd like to give a big thank you to everybody who's contributed in terms of time, advice, money. It's always good. All our technical advisory board and everybody who's just supported us along the way. I'll obviously be around for the rest of the day, or else there's our website and mailing list for further discussion. And we'll also soon be hiring for another member of our team at the University of Cambridge Computer Lab. So a full proper job advert will go out for the next couple of weeks, but in the meantime, please do send informal inquiries to Rob Mullins. And I also have a whole bunch of stickers, which I'll stick on a table somewhere. So if you want a low-RISC sticker on your laptop to show how cool you are, then do pick one up. So thank you. Any questions?
Hi, Rishu Nikhil from BlueSpec. Just following on the Raspberry Pi theme, what's your plans for distribution on this? What will it cost when somebody orders it? What will they get? Will they get a chip? Will they get a board? Will they get different variations on this? What's your plan for all that?
So it'll be, again, this is something which is a bit further down the line. Our main current goal is obviously getting this test chip out there, but we're looking at something in the $50 to $100 range. And most likely you'd have two different SKUs, so one which would be without an FPGA, one with an FPGA for people who want to do hardware prototyping. And we're looking at a kind of Raspberry Pi type form factor, ideally with Wi-Fi and Bluetooth. Obviously, lots of things could change, but that's our current thinking.
Will it be a chip that you have to put onto your own board, or will it be a complete
so
system?
we will sell complete populated boards.
Okay.
You may be able to buy individual chips as well.
And you said it's in the future, but do you have any estimate of when you think this might happen?
Yes, so if we manage to hit the tape out of the test chip by the end of 2016, it's feasible to get a production run in the year after that, so about a year after the test chip.
Tommy Thorne, unaffiliated. The memory, why you put 32-bit for the memory bus, which I thought was kind of curious. It seems quite unmatched to the power of the cores. Why?
Yeah, I think we've kind of outlined a baseline specification that we know isn't completely out of whack with what other shipping SoCs do for low-cost kind of application cores. I agree. A 64-bit bus would be much better, and if we are able to provide that many pins, we'd up it to 64 bits. It's just we've outlined a baseline specification that we've, with our back-of-the-envelope calculations, we think we can achieve with a low-cost BGA package. But yeah, 64-bit would definitely be better.